Lab 5, Choose Your Own Adventure by Central Park Tech. Our objective for this lab was to build a computational model that allows us to predict the motion of a footbag, which footbag's path, um, landing in a trash can, just as a basketball lands into a hoop after it is shot. This video is the one we originally attempted to use, but then we found that just shooting a little hacky sack, also known as a footbag, would be easier for our data extraction, and it'd be better to do in Tracker, as you can see here. And we were able to extract data and use it wonderfully. We wanted to compare the predicted motion of the footbag and the observed motion in the animation we get from the code. Actually, the predicted motion is the animation we get from the code, and the observed motion is everything we get from Tracker. Our procedure was the following. We constructed the computational model using data extracted from our real-world example. We tracked in Tracker, as you just saw, and we graphed the data from the motion of the observed data and compared it to our model data taken from the code, predicting the motion of the footbag going into the trash can. Our initial conditions are the following. The mass was 0.05 kilograms. The start time was 0 seconds. The position was 0.007 in the x-axis, 0.07 in the y-axis, and 0.000 in the z-axis. But since Tracker did not allow us to measure the coordinates in the z-axis, that is just an estimate, and we're just doing this for this specific lab because we actually don't know the coordinates in the z-axis, because the ball could have very easily, or the footbag, sorry, could have very easily moved in or out. Not just in the x and y axis, in fact, in the z axis when it was thrown, and it probably did. Anyway, the velocity of the ball was 8.36 in the x-axis, 3.14 in the y-axis, and 0.00 in the z-axis. We defined our origin as the center of our mass right after it was released from my hand in Tracker. The basic physics principle we need to know for this lab is the same as lab 1 and 2, and seems to be a recurring principle in all of physics, which is Newton's second law. We wrote Newton's second law as the final velocity equals the initial velocity plus the F net divided by the mass times change in time, which is just force equals mass times acceleration rewritten so that we can find the final velocity of the footbag at different time intervals, since we are attempting to predict its future motion. From our code, our model looked like this. And as you can see, the footbag actually ends up, in our model from the code, actually ends up going past the trash can. So that could be due to maybe us not estimating the velocity properly when we plugged it into Tracker. The model predictions versus actual data, you can see that we are comparing the x and y components of the position separately as a function of time. The model position, which you saw, increases at a steady rate in the x-axis, whereas the actual position in the x-axis seems to increase as well, but kind of slows off in the end. And this could be due to just us not predicting the velocity properly when we originally plugged it in. And it could also be due to air resistance. And you can see how in the y-axis, the model position goes past, which makes perfect sense due to gravity, because it's going to go past, and that is also due to maybe our errors with the initial velocity of our object. And the actual position breaks down earlier, which makes sense because in Tracker, our footbag went into the trash can and did not in our model. So we want to know, what does this mean for our understanding of projectile motion, because that really is important. So we developed our own what does it mean question. It is important to understand the velocity in the x-axis appears to remain relatively constant in a case of projectile motion, although this would likely not be the case with an object that has greater surface area, like we saw in Lab 2, except that wasn't projectile motion, that was just a falling object, because an object with greater surface area has more air resistance on it because there's more air available to hit it and keep it from falling. The velocity in the y-axis appears to decrease, or rather increase in negative direction, whichever you prefer. This is what we would expect due to the force of gravity. Again, for an object with greater surface area, the effect of the drag force would be greater. And just like in all the other labs, we developed our own what-if question. We said, what if the real initial velocity was different from what we approximated it to be? That's a great question, because if we had done a better job and possibly predicted a velocity that made the ball, or the footbag, excuse me, land in the trash can, obviously it'd be more satisfying. So we said, just for example, what if it was 2 meters per second slower in both the x and y axis? We actually see that the footbag would almost land in the trash can. And you can see this if we run our module just with the velocity 2 meters per second slower in the x and y axis. And as you can see, the ball actually, the footbag actually ends up landing in the trash can just as it does in tracker. So, like I said, it's probably just due to some kind of human error and us not doing a good enough job with the velocity of the ball, with the velocity of